Greetings everyone to day 2 of week 10 of Computer Science 41, and got my wallpaper ready so we can begin. This is in Switzerland, and Swiss ski resorts are a lot more expansive with less well-defined runs, more just like here's a mountain, you can ski on it. Alright, so we got two different things to talk about today. The first is we need to finish off binary trees and how to delete from them in particular. I do have an answer for you about the C++ 20 question that Bazookian had last time. If you make your own operator, three-way comparison operator, the spaceship operator, it does not actually generate a double equals operator for you. So the standard way of doing it is to make both a double equals and a spaceship operator, and then you can have it sorted however which way you want. If you want to sort something name first, then whole number, using tie is a really cheap way of writing that. And so tie again creates a tuple or a struct that just holds these two things, and tuples have lexicographical comparison built in by default, so it compares names lexicographically, in other words alphabetically, and then if that is a tie, it'll tie them, it'll break the tie using the whole number. So yeah, and so if you use the spaceship operator, the three-way comparison operator, you must also use the double equals unless, and this is what's kind of seems weird to me, unless you choose to use the default three-way comparison operator. And so if you make a default three-way comparison operator, which does exactly the same thing as that, it uses the order of the number variables, name first, then whole number. If your member variables are in the order you want to sort them by, then you can use the default three-way comparison operator, and that one does make an equals operator. So it's a very odd language design decision to me. I don't know why one of them would not make the comparison operator, one of them would. Seems weird, but there you go. And so if you want your class to be sortable, add that line to it, C++ 20 and above. And yeah, if you don't have C++ 20, then you would be doing it this way. Okay. So make a less than operator in that case. Okay. Okay, so let's continue with delete. So deleting with 0 kids, with 1 kid, and 2 kids all need to be handled separately. All right, so here we are deleting, insert, finding, removing. All right. So this loop here is actually pretty important, and what that's doing is it's going to go down through the tree to find the node that we're looking for, and it's going to set parent to be the old current. So as current goes down the tree, current moves down, then parent becomes the old current, and then current moves down and parent becomes the old current. So parent will be set to the parent of the node that you're about to delete. Okay, so then there's 3 cases you have to worry about in addition to root. Is checking the version cpp -- version now. You compile it g++ -- std equals C++ 20, like that. Or if you want to compile it using C++ 17, you do it like that, and then it will yell at you because the spaceship operator does not exist in C++ 17. If you want to know what versions of C++ your compiler supports, then you type g++ -- version. You find out this is g++, Sean Connery, g++ 10.2, and then you go into the documentation and find out what versions of C++ it supports and which parts, because they don't roll out all at once. So if you You go to this web page here, and it will tell you when each of the different language features for C++ 20 were available. So G++ 8 and above, 10 and above, 9 and above, and how are modules doing? Yeah, modules are not out yet. So modules are the really important new thing that aren't quite done yet. It's in the standard, just doesn't really have good compiler support yet. Okay, so let's go back into here, and if you're deleting one child, then that's pretty easy. To delete a child, you just set the, it's like this, you know, got 5, 6, 7. If you're deleting 6, then 5's right pointer is just going to point to 6's right pointer. So 6's right pointer was pointing at Mr. 7 here. Miss 5, Miss 5's right is going to point to 6's right. And then you delete 6. So it's pretty easy. We're not handling deleting from the root right now. So if the kid is our left kid that we're deleting, then our left pointer is equal to the kid's left pointer. Otherwise, our right pointer is the kid's left pointer. It's because we're deleting the left child. If we're deleting the right child, deleting the solitary right. Deleting node with one right child. Let's put it that way. Okay, so if that's our left kid, then our left pointer is going to be set to their right pointer. Otherwise, our right pointer is that right? Yes. Our right pointer is set to their right pointer. Okay. Now, the two children case is the one that gets complicated. That's why I held off on doing this. So, so what if we're deleting 10? Huh. We can't just like pop 8 up into here. That won't work. We can't pop 20 up into here. That won't work. So the solution is to get either the number immediately before 10 or the number immediately after 10. So that's going to be either 9 or it's going to be 15. Because we know that it's immediately before, or if we pick 15, the one after, we know that it cannot have a right kid because it's the one immediately before us. So what we do is we switch these two. So we take the value of 9, put it here, and delete this one down here. That's how you delete the node. You actually delete a different node. You delete 10 by putting the value of 9 up into there and then deleting 9. And we can do that because we know that 9 has either 0 or 1 kids, and we can use the previous delete function for that. Okay. All right. Yeah. And so that is that. And so if we got 2 children, then how do we find the previous or the next? So it's like this. If you want to find the next number, and this could be, there could be more, right? Oops. This would be the one right after 9, right? So in order to find the next number, you take one step to the right, and then you go down to the left, x times, or as many times, infinite times. whatever. Okay. So you go right 1 and then left all the way till the end, until there's no left kids anymore. And that will be the number after 9. Contrawise, if you go left 1 and then down right as far as you can, that is going to be the number prior to 9, in this case 8. You go left 1, can't go right at all, so this is the number prior. And the number after 9 is right 1, and then left. Right 1 and then left, X. Okay. Go right 1 and then left to the end. And that's the number after it. Do you do that recursively in case there's more than one child? No. The number after you or the number previous you cannot have 2 children. Cannot have 2 children. Because if it had 2 children, then you would just keep going to the left. Right? So we know that when you get to the end of the line here, there's no left child. So it can either have 1 kid or it can have 0 kids. And so you just delete that and then put the number here. Okay. So you go right 1 down to the left, or you go left 1 down to the right, doesn't really matter. Okay. Now, there is something really important about binary search trees we need to talk about, and that is the notion of being balanced versus unbalanced. So a balanced tree looks something like this. An unbalanced tree looks something along the lines of this. Maybe you have like a branch or something, but okay, so what is the difference here? BST balanced, BST unbalanced. What's the difference? What difference does this make? Well, what is the running time to find an element in a balanced binary search tree? It's equal to the number of levels of the tree, right? If you're going to do insert, if you're going to do search, if you're going to do delete, all of the operations are actually proportional to the number of levels of the tree, right? So on a balanced binary search tree, how many levels of the tree are there? Got 7 elements here. We got 3 levels. If we had 8 more, we'll have 4 levels. If we had 16 more, we'll have 1 more level. 350, that is correct. So the number of levels of a balanced binary search tree is equal to log base 2 of n. Okay? That's if it's balanced. If you have roughly the same number of elements on the left side as you do the right side. It doesn't have to be perfect, but close enough for college. So, yeah, you don't have to worry about sealing. It's big O. Big O, we don't care about fiddly details like off by 1 and stuff like that. And we don't even care about the base, technically. It could be just log in. So for all binary search trees, all of the operations are actually proportional to the number of levels, to the height of the tree. That makes sense? Because if you're going to insert something, you need to find the spot you're going to insert it. In order to find that spot, you have to go down the tree. The number of times you go down the tree is equal to the height. So you've got the height of the tree. Actually, sorry. I should draw the height of the tree this way, because trees go down. Computer science. So the height of the tree is 3 in this case. Now, what is the height of an unbalanced tree? We have an unbalanced tree. If you've got n nodes in it, what is the height of the tree now? If worst case, let's just say all of them are to the right. When could this happen? Let's say that you're building a binary search tree out of sorted data. Does it happen? Yeah, it does. So if you insert 1, followed by 2, followed by 3, followed by 4, what is the height of this tree going to be? If you insert n elements and all of them, it's just the numbers from 1 to n. If you're going to insert n elements from 1 to n in a binary search tree, what is the height of that tree going to be? It's going to be n. It's going to be n. If you insert 4 elements, the height of the tree is 4. 1, 2, 3, 4. If you insert n elements, dot, 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 n elements, the height of the tree is going to be n. And so all of your inserts, searches, and deletes are going to be order n. That's not good. So our big O just got a little more complicated. BST, big O, just got more complicated. So for inserting, search, for delete, if it's balanced, the running time is order log n. For search, it's order log n. For delete, it's order log n. It's fast. Log n is fast. Okay. It's not as good as order 1, but it's fast. If you have an unbalanced tree, order n. Order n. Order n. It's bad. That's bad. That's worse than all of our data structures so far. Log in Japanese, nice. Okay, so bad, right? Now, reading over your linked list competency exams, a lot of students still don't get the big O, and so you have to understand big O in this class. So just to review big O, imagine you've got like a giant data structure. Like it's got like a billion elements in it. It's a giga whatever. And so it'll be 4 gigabytes of RAM, right? You have some giant vector, and it's just filled with data. Okay. What is the running time to push back one element? Do you have to iterate across this whole thing to push back in a vector? Vector dot push. No, usually not. It's a little complicated because it's an amortized operation. But normally there's an internal buffer in the vector, and it just will allocate the new thing there. Every so often, though, it'll run out of room, and it will do a full recopy. But the full recopy happens once every n times, so it averages out to 1 operation. So normally for a vector, you don't have to iterate across all billion elements. You just go to the end and put it there. Now, for inserting at the front of a linked list, let's say you've got, I should draw it that way. Let's say you've got a billion integers in this linked list. Right. Next, in previous pointers, oops, I should draw them the same way. It doesn't. Whatever. You got a head pointer here, got a tail pointer here. This is your standard linked list here. It's got numbers in it. If you wanted to insert at the end of a linked list, is that order 1 or is it order n? And you have to think about it like, do I have to go across every element of the linked list? You know what I mean? Do I have to start at the front and go to the end? If I do, that's order n. If I don't, it's order 1, probably. So it is order 1. It is order 1 because I got a tail pointer. So all I have to do to add a new element to it is say tail points to next equals new, and the new guy's previous is tail, and move tail, and we're done. You don't have to go through the entire list. Now, what if you wanted to save memory? Those 64 bytes of RAM you want to save, and you want to have no tail pointer. You can make a doubly linked list without a tail pointer. It's a little weird. Normally, in that case, it would be a singly linked list like this. if I wanted to push back on this list, is it order 1 or is it order n? And this is why like consulting tables of like big O answers is not going to help you, because you have to understand actually the data structure. And that's why I have you guys write linked lists and mess with pointers and all this stuff, because that's what internalizes it for you. You have to write a data structure really to understand it. And so, yeah, there is no way of getting to the end here without starting at the beginning, going to the next, 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 going to the next n times, and then finally at the end, I should put the ink back on, and then finally at the end, adding a new node here. Okay. So what about inserting at the front? If I wanted to insert, if I wanted to push front, adding to the front of something on a vector, can I do that? I've got data there already. What do I have to do in order to put something at the beginning of a vector? What do I have to do? I'm not asking big O, like what do I have to do? If I want to put the number 42, at the front of a vector, what do I have to do? Assuming I'm not going to erase 5, right? I'm actually going to insert at the beginning, not erase, not replace. You have to move everything to the right. Yeah, 10 moves to the right, and 8 moves to the right, and 7 moves to the right, and 5. So all billion elements have to move 1 step to the right. Now I've got room here at the beginning, and 42 can come in. Okay, so that's why vector push front is order n, because you have to iterate across the entire vector and move everything 1 step to the right, which is a PDEP. Okay. For inserting at the beginning of a linked list, do I have to iterate across the entire linked list to insert at the beginning? If I've got a head pointer. Grace is correct. I do not need to. If I've got a head pointer, all I have to do is say head's previous is the new guy's next is head, and then have head point to the new guy. That's it. I don't have to loop across the entire data structure. This is how you guys should be conceiving of Big O in your heads. Like a lot of people look at these cheat sheets and things like that. Big O cheat sheet, and it's not super helpful because it depends, right? Like inserting, deleting, or order 1 on a singly linked list, is it? Worst case, order 1, is it? I don't know. I don't think so. Right? Because if you don't have a tail pointer, you can't insert at the end. You know what I mean? And if you want to insert at the middle of a linked list, if I want to put an element in here, it depends if I have a pointer to here already. If I have a pointer to here, then I can insert it very easily by just kind of hooking up the pointers like that. It's order 1. If I do not have a pointer to here, if all I have are the head and the tail, then in order to insert in the middle, I have to iterate, go to the next, 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 until I found the place that I want to insert, and then I insert. And so you have to read the question, you have to understand how the data structure works, and then you can answer whether it's order, like inserting in the middle is sometimes order 1, it's sometimes order n, right? It depends if you have a pointer to the place where you're going to insert or not. Okay. Inserting in the back depends if you have a tail pointer or not. You know, so order 1 is always the best, unless you consider order 0 to be better. Yeah, order 1's always better than order n. It's faster. We always care about speed in computer science, unless you're the DMV, in which case, if you get paid, let's see, when would that's actually a good question, Mr. Yui. When would it be better to do order n versus order 1? Let's say that you're IBM and you are leasing out mainframes to people, and if they saturate the mainframe, you sell them another mainframe. In that case, make sure it's order n, so that at the beginning it looks like it's really fast, and then over time it'll slow down. So you're like, you need a new mainframe. You sell them 2 now. It's twice as fast now. And then over time it gets slower. You need 3 mainframes now. Big brain, right there. Stonks, yes. Sounds like an Apple thing to do. Yeah, Apple would slow down their old devices. Oh man, this thing's really slow now. When you buy it, it's all snappy, and then they push out patches that slow it down. You're like, oh man, this thing's... Yeah, computer doesn't age like people do, you know? Like, chips don't get arthritis, you know what I mean? And so when your computer becomes slower over time, you know... It's not... Because it's old, usually. I guess in theory it could start overheating or something, like if the heat seat came off or something, like I guess in theory it could slow down, but they don't age, you know. And so when your computer starts running slower and slower, maybe it's because you've installed a lot of software on it, or you have spyware or something. But in general, if you haven't messed with it, it shouldn't be going slower. That's just Apple trying to sell a new product. Pretty shady. We need those right to repair laws, yeah. Okay. You never actually own your device when you buy from Apple or, you know, Microsoft nowadays. You don't really, even though you're the administrator of a Windows PC, it still doesn't allow you to do everything you want to do. All right, now, so for a binary search tree, you have to understand balanced and unbalanced binary search trees are going to give you different big O performance. If I'm going to be inserting on the bottom of this ungodly monstrosity here, if I'm going to be inserting 9 million, it's going to go to the right, 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 and then at the very bottom it will insert 9 million or whatever, right? So for a unbalanced binary search tree, the running time is terrible. This is like worse than everything. Right? This is worse. This is a worse running time than like literally, you know, all the other data structures we've looked at. So is there a way of guaranteeing that your tree is balanced? What do you guys think? So is there a way to make sure that you never get this, so that even if they insert 1, 2, 3, 4, 5, 6, is there a standard library function to reformat BSTs? There's a standard library function that does BSTs. And so when you're inserting into the standard library, 1, 2, 3, it will do what's called a rotation behind the scenes. You don't notice this. And it becomes 2, 1, 3. Yep. So this is how the set class works in the standard library. So as you insert into it, if you then insert 4, 5, 6, normally you would get, you know, this big 4, 5, you know, 6. You get this horrible unbalanced tree. You insert 4, it comes over here. That's fine, I guess. You insert 5. It doesn't like that, so it will do a rotate. Let's see, now what do we have? 3, 4, 5. So you have 4, 3, 5. Then if you insert 6, the 6 will just go in there. So if you ever have one of the branches be more than twice as long as another one, then it will rotate. We'll clean it up. And that's just pointer stuff. So this is a junior level data structures. Yay, you don't have to do it in this class. Okay? But it's just messing around with pointers. So if you thought that this is the last class you'll need to know pointers in, you're wrong. You're wrong. So what happens is 2 would point to 4, and 4's left child would point to 3, and 4's right child would point to 5. And so that would go away, that would go away, and I guess that would be left alone. So it's just a little bit of rotating. It's actually not that bad. You just do some pointer shuffling. But because people are terrified of pointers, this is a junior level thing you gotta do. And then yeah, it does get more complicated if you have to rotate multiple things, right? If they have kids of their own, then yeah, like I said, that's a junior level thing. Don't worry about it. Just conceptually, all you have to know is that the set class does it for you. Okay? So if you want to use a guaranteed balanced binary search tree, use the set class. Easy. Call insert, call search, call delete, remove. Okay. So that's the level that you're at right now. I would just use the set class. I wouldn't write my own. You're gonna have to write your own for the homework assignment after the current one. But that one is supposed to be unbalanced. You can't use the set. You cannot use the set for the upcoming homework assignment. It needs to be unbalanced. There's a reason for that. But yeah, in general, you're going to want to use the set class, especially at the level you're at right now. Why write your own? It's complicated. Okay. So one of the things... Okay, so basically, coming back over here to the table of Big O, the Big O table, if you make your own binary search tree, you have no guarantee that it's going to be balanced, right? And so this is you, unfortunately, right now. Until you take junior level data structures, any binary search tree you create will be order in, worst case, insert, search, and delete. So my advice to you guys is if you want to use a BST, do what I do and don't. Use the set class. Okay. There is one really important caveat with it, though. And that caveat is that when you put something into a binary search tree, you can't modify it. Moya, you remember that? You remember how, yeah, once you put something into the set, you can't change it. It's set to be const. So I'll show you guys a way around that in a second. But for your tests and things like that, you need to know these words. So whenever I ask you what the running time of a binary search tree is, look for the word balanced or unbalanced. Okay? So if I say, what is the running time to insert something into an unbalanced binary search tree, what would your answer be? Yeah, if you ever hear unbalanced, it's going to be ordering. Right? For any quiz question that says unbalanced. If I say, what is the running time to insert into a balanced binary search tree, you would say, good. And if I said, what is the running time to delete from the set class in the STL, standard template library, also known as stood. Yeah, basically every operation on a BST in the standard library is order, login. Maybe size might not be, like if you want to get the size of a binary search tree, you might cache that. This might be order 1. Printing a tree is always order in. You know, there is that. So if you're going to print all the elements, you got to print all the elements. There's kind of no way around that. That might be a good trick question for you guys. What is the running time to print a balanced binary search tree? In. Right. You still got to print. You know, there's no way around it. You know, you got to print all the elements out. There's no. Yeah, you can't break time. When will the second quiz linked list be up? I'm gonna work on that maybe tonight. Okay. All right. So it's important though for you guys to understand the difference in running time between vectors and linked lists and binary search trees, because that will control what data structure you use. What data structure you use depends on the needs of your program. What are you keeping track of? You know, what are you doing a lot of? Are you doing a lot of inserts, searches? You know, searching through a linked list or searching through a vector is going to be order in, unless they're sorted already. Searching through a binary search tree is much faster. Binary search trees are good at searching. It's in the name. Okay. So, yeah. If you need to preserve the order, so in other words, you need to keep track of the order that people arrived. Like you got a VIP list, you can't use the BST. A BST destroys the order they arrive in, right? Because it sorts it by name or whatever. So you can't use a BST to do like a queue or a stack. Okay. So, all right. So let me show you guys how to use the standard template library thing. So we got our battleship thing here. We've got this tree class. You can see it's kind of a pain in the ass to write. So rather than doing this, the tablet out of the way. So to that, we're going to make a set of battleships named Battle Sloops. So set is the name of the header file, believe it or not. If you want to use a set class, you need the set header file. Okay, and so this will make a binary search tree. Now, let's say that I'm you guys and I don't remember how to insert, search, and delete from the set class. Where should I go to look it up? Where should I go to find the name of the functions to insert something, to search, delete it? Good. cppreference.com is the correct answer. Don't say c++.com. That is wrong. Okay. So under cppreference.com, you can just search for set, or if you go to the containers library, here, the containers library talks about the data structure. So these are all of the data structures that are in the standard library. And you guys know most of them already. Array, vector, dec, singly linked list, doubly linked list, binary search tree, and map is the only one you don't know yet. Actually, yeah, it's a binary search tree also, but little twist to it. We'll talk about maps later. And then this is the one that you don't know, which is called hash tables. That's the last major data structure we're going to learn in this class. And then you know about queues and stacks. You don't know priority queues yet. That is a heap data structure, which again, you don't know yet. So, yeah. So you guys actually know most of the standard library. It's two data structures, 2.5. It's map. A little bit of a trick to it. So we're going to click on the set class here. And scroll down. It tells you the header file that you need. You scroll down, and it will tell you all the different functions that exist in the class.
Okay.
Yes, girl.
The time goes for you.
The time goes for you. Okay. So, not too many functions. Clear erases the tree. Insert puts something into the tree. In place does the same thing. Erase is the delete function. So insert, search, right there, and delete. So those are our 3 functions. Okay. That's it. That's all you need to know. Count will tell you how many. Count's going to return 0 or 1. Is something in the tree or not? It's basically that Boolean search we did before. And then find will actually return an iterator pointing at the element in the tree. Do stuff with it. Okay, so yeah, that's all that really matters. Okay, so snap that over there. Snap that over there. All right, so we've got a stood set. We're going to read a battle sloop from the keyboard, and yeah, rather than just printing it out, we're going to add it to our set. So we're I don't want to type that. I'm going to call you BST. 3 letters. BST.insert. Okay. So So that will add the battleship to the. We'll add the battleship to it. Let's make it a little more interesting, I guess. So we're going to have the name, the whole number, and the crew complement now. We'll make the double left arrow a little more interesting. It will print out the name is this. The whole number is this. And the crew complement is this. You know, I don't want to write crew complement because I'm actually going to keep track of how many crew it has. And so, one of the nice things about using the default comparison operator is that it will just compare these things in order. So if there's a tie on the name, then it uses the whole number. If there's a tie on the whole number, it uses the crew to sort. So, neat. So I don't have to update this every time also, which is also one of the nice things about C++20. Is this a government contract? Is there a shortcut to divide the screen and place both files next to each other? Windows key left arrow, Windows key right arrow, left arrow, left arrow, right arrow, right arrow, left arrow, left, up arrow, down arrow, down arrow. Yeah. So, or you can just snap it to the side by throwing it against the right edge of the screen. Left edge of the screen's a little tricky because it'll just go across because I got two windows here. But if you move it right up to the divider, you see a little border appear there when you touch the edge, and it will snap that way as well. Okay, is this a government contract? No, we're trying to do fast. We're trying to make it go fast. Okay, so let's do this. Okay, so please enter the name of a battleship and a whole number. Okay, and we need and crew and the crew battleship. Let's see, enter the name of the battleship. The whole number and crew size 0, whole size to quit. Okay. And so after we're done with this, the first thing, what should we do after we have inserted into a binary search tree to make sure that it works? Right, we haven't tested this code yet. Hollywood probably thinks code looks the way they depict it because they saw a programmer simply perusing down their code at one time and it stuck. Yeah, this is how Hollywood thinks that we program. Emma is correct. We need to print it out, right? The first thing you should always do after any time you've inserted some things into it, always print it and just make sure they appeared there. Don't trust that it works right. So before we had a print function. Is there a print function on the set class? There's not. There's no function to print it. If only it had iterators. If it had iterators, then we could use a range-based for loop with it. It's got iterators. That's cool. So what we can do is say for every battleship. And again, always do things const reference unless, you know, you need to modify it or something. So for every battleship B in the binary search tree, cout B. Okay. You're like, well, wait, doesn't that look just like printing out a vector? Yep. Yep. Isn't that just like how you print out a list? Yep.
Because you are printing out a list?
Nope, because I'm printing out a tree, but the C++ language has made it very easy for you to switch one data structure out for another. So if we compile this, nope, wrong one, G++, BST. The main is hole 10, 1,000 people. The Iowa is hole 42 with 2,000 people. And then we'll have the main with hole number 40 with 50 people. And then we'll have the main with hole 40 with 500 people. Oh, shoot. 0, 0, 0. Okay, there we go. And so you can see it is sorted alphabetically first, right? So it has sorted the battleships by name. And then when there's a tie, it sorts by whole number. And where there's a tie, it sorts by crew complement. You guys see that? And that sorting was done using this C++ 20. Yay, cool. If you don't have C++ 20, you've got to write that less than operator. You got to do that. And every time you add a new member variable, you got to put that in there as well. Okay, any questions so far? So yeah, that will dump the entire binary search tree. Any questions? And if you want to change how the thing sorts, if you're using the default comparison operator, you just do it like that or whatever. Then it would sort by whole number first. Okay. So what should we do next? What should we do next? So we're inserting something into a database, essentially. We're printing it. What should we do next? Empty it? You want to delete it? No. Let's not delete it. Or not delete the whole thing. We can delete one thing if you want. Remove? Sure. All right. Let's make a menu. Let's make a menu. So while true, cout. Ooh, one of my former students messaged me last night, and he doesn't like cout statements. He's like, could you make it easier for me to print things out? So, yeah, sure. Right. Void print auto x cout x in y. How about that? This is also C++ 20. If you don't have C++ 20, it would be this template class t void print tx So, do you see what's happening here? So we made a print function that can take any type, and it's just going to cout that type, or that variable of that type. Okay. Make a write library, print library. And so there you go. And so, maybe you want one version that just prints the thing. Maybe you want one thing that print line or something like that. And print line. Make it like a Python up in here or something. So we can do this. Print line one insert new battleship. To delete a battleship. Search for a battleship. What else should we do? Maybe have two battleships fight each other. Five print and battleships. do you think? Okay. What do you guys think? Would that be interesting for you? Do you want to see me implement this really fast? Cool. All right. So just as a fair warning, your next homework assignment is going to be doing something along this lines of complexity, and you should use the set class probably, maybe, I don't know. So pay attention. You have 2 days to do it. So there we go. We got this, and we should probably also have a quit as well. What did I just say? You'll have 2 days to do the next homework. It's easy. Don't worry about it. No. It's not a joke. It's not a joke at all. Okay. So, int choice equals read type choice. And then if choice equals 1, thought you said we couldn't use the set class. I said the homework after the next one. Homework after the next one, you can't use the set class. This one's just a little itty bitty coding assignment just to give you guys some free points. I used to do the assignment I'm about to give you guys in class, so students would have an hour to do it. So it's not hard. And one of my goals in this class is to make sure you guys can code your way out of a plastic bag. And so you don't have to know any of this pointer stuff. You just have to use the set classes. Make your own class and make it set out of it and insert stuff into it and search it. That's it. It's not bad. Okay. So all right. So okay, choice 1, please enter the name. Okay. So 2, to delete a battleship. Else choice equals 2. To delete a battleship, we will be using the erase function. Does this take an iterator? Yes. Can we use the key to delete it? If the key equal to key. Okay, good. What are you complaining about here? Out of the if. Else if choice equals 2. Good. Okay. So if choice is 2, we're going to erase. So we're going to say BST dot erase, and we are going to we need to get a battleship. Please enter the name. So in order to delete it, you must have exactly the right name, whole number, and crew complement. But there you go. So that's how you insert something into a binary search tree. That's how you delete something from a binary search tree. All right, search for a binary search tree. So count returns how many times that battleship appears in the that shows how many times the thing appears in the tree. So it'll be 0 or 1 because sets don't allow duplicates. So pretty easy. So if it is in there, then print bound. Yes, it is in the set. It is in the BST. Else. No, it is not in the BST. Okay, so that's how you search. So we got insert, we got delete, we got search. Those are our basic things. How do we fight two battleships? Let's, no, we need this as well, of course. Else if choice equals 5 to print it. Stuff that in there real fast. Then otherwise, break. Okay. So let's see if this works. So we're going to insert new battleship, the Iowa, whole number of 40, crew size of 2,000. Insert a battleship, the Maine, whole number 42, crew complement 1,000. And then print the battleships. We got the Iowa and the Maine in there. Let's delete a battleship. Iowa, whole number 40, 2,000. Print the battleships. The Iowa's gone. Search for a battleship. Iowa. Nope, not in there. Search for a battleship. Maine, 42, 1,000. Yes, it is in there. Print. Okay, so the only thing we need left to do is to fight the battleships. Okay. Can we have more than once with different values? If they are identical to each other, you cannot. If I were to insert the Maine again with hull number 42 and a crew complement of 1,000, you will see that when I print it, there's still only one Maine. If you wanted to have duplicates allowed, you would use the multi-set class. So multi-set allows for duplicates. It's the only difference. So with multi-set, count could return more than 0 and 1. Right? For a set, count is going to return 0 or 1. It's essentially a Boolean. Right? But for multi-set, it can return a 0 or a 2 or a 5 or whatever. So the multi-set keeps track of how many times you've inserted the same thing. And if you delete from it, it just decrements the count until it hits 0. When it hits 0, it erases the node. Okay, so that is pretty good. Now, we're going to run into trouble, though, when we try fighting our battleships. Okay, and the reason why we're going to run into trouble when fighting the battleships is because we can't modify nodes already in the binary search tree. And there's two ways around this. So let's say that when two battleships fight, it just subtracts the crew complement of the smaller one from both of them. Right, so the smaller one gets destroyed, and the bigger one has it, like the Iowa with 2,000 would go down to 1,000. You guys understand? So if the Iowa had 2,000 and it fought the Maine would be destroyed, and Iowa would go from 2,000 to 1,000 because Maine had 1,000 soldiers on it. Does that make sense to you guys? Okay, good, because you're going to need to be able to do this for the next one or so. All right, so how do we do this? View, then bst.cc. So else if choice equals 4, okay, so battleship temp, please enter the name, crew size to fight, and then we're gonna just check to make sure that it's in the we're gonna just check to make sure that battleship exists, right? So if the count equals 0, Can equals 0, we'll just continue. Continue jumps up to the top of the loop and starts over. So we should probably print an error message as well. Sure. Print line. And then we'll do this again. 1, 2, 3, 4, 5 lines. And so we'll have temp and we'll have temp2. Okay. So we've got our 2 battleships. Now, we need to figure out which one has the smaller... What's the matter, bro? You're making weird noises. Okay. We need to figure out which guy's going to lose. Right? So, Boolean... temp... temp1... Boolean temp1 1 temp1 1 is equal to temp1 dot crew. Ooh, what about a tie? Then they'll both die. All right. So first of all, if there's a tie, then we'll just delete both of them. That'll be easy. So if temp1 dot crew equals temp2 dot crew. Print line, they blow each other up. And then we will just do the BST dot erase, temp1, temp2. You guys understand? So do you see how easy it is to use data structures in practice? So, all right, we've got these 2 battleships in there. Let's take them out. It's way easier to use this than it is to do all this stuff with the pointers and think about the different... Go to the right and then go to the left. And could you just keep hitting the same spot till the crew reaches 0? I don't know what you mean by the same spot. Temp1 and Temp2 are the battleships, yeah. So we are going to read a battleship from the user, and if the battleship's not found, we return. So this is actually a separate variable. This isn't actually in the data structure. It's just a temporary variable we made of type battleship. And what erase does here is that it searches for a matching key in the BST, and if it finds it, all right, we can do this the more proper way, but this way will work. So this will erase the matching key from the binary search tree. Okay. Temp1 and Temp2 are the battleships, yeah. Or the 2 battleships, or they're copies of the battleships in the binary search tree. Okay. If we wanted to get the actual battleships in the binary search tree, which we probably should do, we need to use find. So find is going to return an iterator. It's like a pointer. Okay, so we'll do that instead. Auto iterator 1 equals bst.find, searching for temp1. And then if the iterator, if it was not found, the iterator, if iterator 1 is equal to bst.end, that means if it doesn't find anything, then it returns end. Like that. So there's a special pointer off the end of the data structure that it returns if it's not found. Okay, so then we could use the iterators to destroy the binary search tree. Does exactly the same thing, but this time we actually have a pointer to the element, so it doesn't have to do the search again. It just, here's the iterator, and it takes it out. This will be a little bit faster, because the other way would have to repeat the search. Do you guys understand? And so this is a pointer, and that's a pointer to the elements in the binary search tree, essentially. Okay. So we've handled the tie. Now how do we handle the other options? Okay. So if temp1 crew is less than temp2.crew, then cout iterator2 dot name destroys iterator1 points to name iterator1 points to name. So you see how you can use these iterators like they're pointers. So
I think Ender put up a good point. For it too, you're finding temp1.
Oh, copy paste. Thank you. Classic mistake. All right. So if you want to do it this way, then that gives you a pointer into the data structure essentially, and you use the arrow operator like we've been doing so far. So that's how you can access the name that way. Or I could write it like this. These two lines of code do the same thing. Okay. Okay. You guys see that? We made a temporary variable that is a copy of, this is not the person in the binary search tree. This is just a new variable we made that's got a name, a whole number, and a crew size. And we search through the tree to find a matching one. And so this is the guy actually in the binary search tree. That's a pointer to the guy in the binary search tree. Over here, temp1 is just another variable. It's not in the tree at all, and we're just using that to find the one in the tree. And so you can pass erase either the pointer to the guy to delete, or you could pass it the copy, and it will find a matching guy to the copy and delete it. Either way, it'll work. Okay. Which way is better? Using the iterator is faster because otherwise the code's going to have to keep searching. Every time you do something, it's going to have to search through the binary search tree and find it over and over again. So this will be faster because you have a pointer to it now, and then you just call erase without having to go through millions potentially of battleships again. If you don't have many battleships, who cares? It's not going to make much difference. But just notice the difference in syntax here, right? Temp1 is a variable that is the duplicate of an item in the binary search tree. Iterator is a pointer to the person in the binary search tree, so you use the arrow operator to point to it. Same thing. It's the exact same code, two different ways. Okay, so if temp1 crew is less than temp2 crew, we do that. And then temp1 is going to be destroyed, bst.erase iterator1. And then what we want to do is we want to say iterate, before we erase it, we want to say iterator2's crew minus equals iterator1's crew. Do you guys understand? So if the main had 1,000 soldiers and the Iowa had 2,000 soldiers, then the Iowa is going to lose 1,000 soldiers. Do you guys understand? This is where the battle takes place. It doesn't work. This code does not work. And the reason why this code doesn't work is because the BST sorts the BST based on, in part, the crew. And so if you were able to modify the name of the ship, it wouldn't be able to find it anymore, right? Like imagine I changed the name of the ship, right? Iterator2 points to name equals ZZZZZZ, right? So somewhere within that binary tree, you've got a binary tree. If you could modify it, 5, 10, 7, 20. If I could modify this to be 100, it breaks the binary tree. You know what I mean? Like, that'd be really bad if you could modify it. So binary trees are what are called immutable. Okay. So you cannot modify elements in the binary tree, especially when you're actually sorting on them, right? So there's two options here. The first option is to make it not sort on the crew. The second option is to delete it and then reinsert. Right? And so the easier option is to delete and reinsert. So let's do that. Mutable is a okay. So what we're going to do is we're going to take that duplicate we had, that guy. So we're actually going to delete. We're actually going to delete both of them. Okay. We're actually going to delete both of them, and we're going to insert a new one. So temp2 temp2.crew minus equals temp1.crew. Remember, temp is just a variable. It's not part of the binary search tree. It's just a variable that is used to match in the binary search tree. And so we can't do this. Can't do this since a BST is immutable. Everything is constant in a BST. Once it's in the tree, it is immutable. You can't change it. All you can do is delete it. Okay. So we can, however, delete the two that are in there already and then insert the modified one. So we can insert temp2 bst.insert temp2. Okay. Y10Y, Shift P. Nope, one too many lines. Y9Y, Shift P. There we go. And then we'll just make this an Elsa, Anna and Elsa, and just change all the 1s to 2s and the 2s to 1s, and call it a day. I'll leave both versions in. There you go. So I'm actually erasing both of them out of there, and then I'm putting the changed version back in. Any memory leak you should be concerned of? No. All of these standard library containers don't leak memory. It is almost impossible. If you really try, you can make them leak memory, maybe, but they cannot leak memory. Yeah. So is this the drawback of the BST? Yeah. It's an annoyance. You can work around it. You can work around it by marking a member variable as mutable. That will allow you to change the crew. So, hit 1 points to crew, minus equals hit 2 points to crew. And then I don't need to erase and reinsert. Okay, so these are two different ways of doing the same thing. So one way is you erase both of them, or you, if you want to change something, you just erase it and insert the new one. This is the easy way. Tricky way is by make crew a mutable, and then that allows that to work. If a member is marked as mutable, are you no longer able to use it as sort? Correct. That's why I said it's tricky. This is being used to sort right now. It'll compile its now undefined behavior. So I cannot use my cool thing anymore. I, however, can use my old ones. My old ones don't use crew count. You see that? That's why I left them there. So my old ones sort based on name and whole number. They do not sort based on crew count. Therefore, this is actually a-okay. This is fine. The reason why it doesn't allow you to modify a BST is because if you break the thing that you're sorting on, it breaks the BST entirely. So, if however you have some other variables in here that you're not sorting on, feel free to modify them. So you mark them as mutable, and then you can do that. So I recommend you guys do it this way. So as you modify your data structure, you are going to, if you want to change a BST, erase something and then insert the changed copy. Are you guys with me on this? So we've got a node in the BST that's got 2,000 crew in it. We reduce its crew by 1,000. We erase the old one. We erase the ship that sunk. We erase the main. We then erase the old Iowa and put the new Iowa back in with the less crew. So the easy way to modify. So, what do you guys feel like? Does making it mutable make it ignore sorting on the variable? Nope. Just means you can change it. So it's up to you. Mutable is an advanced keyword. So it's up to you to make sure that you are not sorting it using a mutable variable. So Edgerlin, let's not worry about this part right now. Edgerlin, do you understand this part? Where were we? Do you understand insert, erase, count? Do you understand those three functions? Insert will add to insert adds to a binary search tree. Erase deletes from a binary search tree, and count tells you if something is in a binary search tree. Those are functions for the BST class. Yes, it's not called the BST class. It's called set. Okay. So if you want to make a data structure of battleships that's a binary search tree, do it like that. You don't have to call it BST, by the way. Set is used inside the battleship struct, other way around. This is a set of battleships. So the set holds battleships. Battleships don't know anything about being within a set. They're just a value type. They just hold a name and two ints. So yeah. The three things you guys have to know: how to add something to a BST, Bazookian said count returns Boolean, right? No, it returns actually an integer, but the integer will be 0 or 1. So it's effectively a Boolean. But the actual type of it, I think, is the size underscore t. So it actually returns an unsigned 64-bit integer that will be either 0 or 1. Yeah, it will be 0 or 1, but I believe the type on it is size t. Yeah. So it's gonna return a 64-bit unsigned integer that will be either 0 or 1. It's called count because that way you don't have to rewrite your code if you change it from set to multi-set. That's why it does that. Keeps all the code the same. They really want you to make it easy for you to switch data structures. Okay, so what is your 48-hour assignment? Dun, da, 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 da. Dun, da, 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 da. Da, 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 dun, dun, dun. Okay. So for this assignment, it's basically going to be what we just did in class today. 48 hours. Yeah, well, a little less. 46 hours. So, you are going to implement a Elo calculator. Elo is used for computing the rankings of chess grandmasters. Well, actually, everybody in chess that play ranked games in chess. So, other systems use either Elo or similar ideas, where basically it tries to match you with people of equal strength to make gaming more fun. League of Legends uses what's called MMR, Heroes of the Storm, Overwatch. They all have various versions of the Elo system that gives you a ranking that tells you how strong a player you are. Ironically enough, Tinder does as well. Tinder actually will try to compute how attractive you are and match you with people of equal attractiveness. So I've never used Tinder, but I could just imagine like being like, oh, wow. Not pretty, am I? Bruh. Yeah. So, you are not going to code chess. You're not going to code League of Legends. What you're going to do is just do an Elo system. And so, basically, there's two parts to this assignment. You can work on it with a partner if you'd like to. You don't have to. This is going to be auto-graded. Each partner has to have their own copy of the code. So make sure, you don't just have it on one person's account. The way I recommend breaking this down is have one person do the Elo calculations. The Elo calculations are just algebra. So basically, you can read through how Elo is calculated. There's a K value, and that's how many points are up for grabs, and and then the other person should work on the data structure side of things. So you are going to input over and over again a player. And so you're probably going to need to make a class for holding a player, a chess player. Okay? Kind of like our battleship class. Hey, okay. And every player is going to have a name, an address, an ID number, and an Elo rating. Okay? And you're going to repeatedly insert those four things over and over again until the user types done. Okay? Then the input phase is over. Now you're going to enter the playing phase. And in the playing phase, you are going to it'll give a player ID 100 faces off against player ID 200, and it will say if player 1 won, player 1 lost, or player 1 drew. Okay? And so what you need to do is update the Elo score. Just like the crew number, you need to update the Elo score for each of the players. So basically, you're going to so whoever wins points are going to transfer from the loser to the winner. That's how the Elo system works. So you can do that either by deleting them out of the BST and reinserting them with the changed numbers, or you can make the Elo value mutable and just do that thing I showed you there. If you're going to ask, am I going to make the BST publicly available for you guys to steal from? Yeah, sure, why not? So copy bst.cc. Where am I? Copy bst.cc into public and make it world readable. Okay. So basically what we just did today with the battleship thing, you're going to do something similar to it. Right? You're going to have a name, address, things like that. Okay. And then in phase 3, you output the person who had the highest Elo rating. Okay. So if your BST is sorted on Elo, then it has to be immutable. Then you can't make the Elo score mutable. So maybe, I don't know. Will there be an input tester for it? Yes, there is an input tester. It's already up. Okay. So what I would recommend is have one person work on the algebra side of things. They get the algebra working right to see if a person with an Elo of 1,000 fights a person with an Elo of 1,200, how many points get transferred. There's a little bit of algebra involved in that. And then the other person should make a class for holding player information. stuff it into a BST. You don't have to use a BST if you don't want to. You can use a vector, but you're going to not pass some of the test cases because the test cases are time-limited. Time-limited test cases. So if you use a vector or a linked list, you are going to explode the time budget. It's not going to work. You're not going to get 100%. So, yep, you can just copy one set to another set. Okay. And first group to finish the assignment, we can't do because this is asynchronous technically. Sorry. Yep, sorry, we can't have a competition because we don't have a regular class. But yeah, let's ignore in Corona world. Sorry, no extra credit on that. But all of you guys should be able to do this assignment, even individually. Okay. So that is in the Elo. Folder. Make sure you put the name of your partner at the top of the file so that you don't get flagged for cheating with them. Okay. What if you finish today? It doesn't matter because it's asynchronous. So we cannot require that somebody be watching it today, right? So somebody should be able to watch it tomorrow and still have an equal opportunity to get the grades. So unfortunately, I cannot do a time-based competition with this. If you finish, this should take you hour and a half, maybe hour. Like I said, I normally do this as an in-class competition. So this is designed to teach you guys to code quickly. You need to be able to code your way out of a wet paper bag. That's one of the requirements I have for this class. You should be able to make a class, stuff it into a data structure, search the data structure, modify the data structure, and then find the top player, Magnus Carlsen or whoever. Just use the set class is my advice to you guys. Okay. So yeah. This will be a good assignment for you. You got 46 and a half hours. Go. I have stuff today, so I'll try to time myself for that 1 hour tomorrow. Yep. Insert, insert, find. Count, maybe. You can work on this either individually or with partners. That is correct. You will not see it on Canvas because it is going to be individually graded. There's an auto grader. It'll just grade everyone separately. Yeah, if you want to work with somebody, knock yourself out. Sure. Erase. There's no erase. I don't think you need. Yeah, you might need erase. Yeah. If you're going to be pulling it out, changing it, and then putting it back in, you'll erase and then reinsert. Or you can do mutable. All right, begin. Make for the command, I think so. Yeah. There's a make file. I split up the files so that there's one file for the Elo person and one file for the class. Okay, any questions? That's it for class today. Good luck. Have fun.